First of all, good morning. Thank you for the organizers for selecting my talk so I can present it here. This is work I have been doing in a collaboration between the University of Brazil and also in Barcelona with Isabel Zon. And today you have been hearing about improvement in phases, combining partial solutions, and here I'm actually trying to improve place fragments by a multi-solution sidechain extension. A lot of people talked about phasing macromolecules from fragments. Archimboldo uses the strategy of locating fragments with phaser. Those fragments are usually ubiquitous to proteins, such as α-helices, beta sheets. They can come from libraries. They can be shreds of remote homologous structures. If the fragments are close enough to the real structure, then SHELXE may perform density modification and autotracing and review the rest of the structure, such as this picture shows. But this second stage may fail if we have errors in the fragment location, if we are dealing with a large structure, but we only have an initial fraction of the coordinates, if we're dealing with medium to low resolution, if we have low solvent content, if we have high beta sheet composition, if there's pathology on the data. This scenario is shown here in this structure, LMTC. This structure, the initial data set that we had when we were phasing the structure was diffracted to 2.7 angstrom. It has a pH1 space group, 2 monomers in the symmetric unit. This dimer is composed of 684 residues. So if you look here, this is the final structure. Right now, the PDB code has a higher resolution data set, but this was the one that we used to solve. This monomer is composed of 2 domains. The first domain is the C-terminal domain, and the other domain is N-terminal domain, which we didn't have any target structure. The C-terminal domain, it's almost half of the protein. It shares 40% of identity with the structure LMTE, and they shared 0.8 angstrom RMSD. We obtained a partial solution using this structure. We truncated the side chains, and with the polyala model, we were able to correctly place these 2 monomers. But when we try to expand this partial solution and review the rest of the N-terminal, we did not efficiently obtain the rest of the structure. Even if we could place new fragments into this missing N-terminal domain, the electron density map didn't show us additional features. So here I'm generating a map after density modification of those placed fragments and from the original placed C-terminal domains. And if you look at here, in sticks we have the located fragments, and in ribbons we have the final structure. And in this region we may see that the electron density doesn't really show us additional features for this additional strand. And if we look at those fragments of the α-helices, here we only had the polyala chain, and these sticks are the final structure. Even we are lowering the sigma, we do not see a strong signal for example, the side chains. We only see the signal for the electron density for the main chain. And so our idea was we raised the hypothesis, would the sidechain completion again be the necessary information to allow expansion success? So in this case, other algorithm would address this question by trying to fit the electron density, the side chains in the electron density. But in this case, in this resolution, with this partial solution, we didn't have such information. So our idea was to use all of the necessary information that we had based on the sequence and based on the sequence from the C-terminal domain, and generate different hypotheses and extend this partial solution with all of the possible side chains that we thought it was feasible to calculate. So we developed a remote homolog mode. We start from a partial solution, such as the case that I showed you before. we can have a partial solution from Archibald or Schroeder. The way that we use libraries, we use rigid bar refinement with Jimbo in Phaser, so those fragments may be displaced. So sometimes we can place a helix correctly, but then this rigid bar refinement may shift one whole turn or may shift a little bit. So we cannot entirely believe on the sequence match in the alignment. So here we have the remote homologous sequence and the target sequence. We have the perfect match, and in sequence slider what we do is to take this alignment and match and then generate different hypotheses, sliding, choose sliding window to the left in this case and choose sliding window to the right, and then we have for these 4 fragments, 2 alpha helices and 2 beta strands, we have 5 hypotheses for each fragment. We may combine those different hypotheses in a total of 625 combinations. So this is sequence slider workflow. We start with an input, an alignment, and the fragments. We generated all the hypotheses, all of those possibilities of the sliding. The number of slides that we do and the number of hypotheses is set up in the program. We model all of those hypotheses into the fragments using the software Squirrel4. So this software has a rotamer library. It uses the most probable rotamers and also uses an energy function to decrease the clashes and so on. So we generate all of those models. We refine them using either Buster, PHENIX.REFINE, or REFMAC. We score those models with LLG, and LLG serves to filter the best hypothesis, and we perform density modification and autotracing with SHELXE, and if we got an improvement, we may review the rest of the structure. So we applied such a strategy with the LMTC. In these plots, I show in the y-axis the percentage of identity of each hypothesis. Each hypothesis here is shown as a dot. In the x-axis, we have the LLG. And here, in the coloring, it's the weighted mean phase error that we calculated with SHELXE using the starting model. So here we can find the correct solution. It has a higher identity than all of the other hypotheses. Since the C-terminal domain had almost half of the total structure, it has an identity close to 50%. So so we use LLG. LLG in this case is not an absolute value, but a relative value that we use just to differentiate different models. And here we submitted all of those best score models to SHELXE expansion. We obtained, for the best hypothesis, a correlation coefficient of 36. It improved the weighted mean phase error to 55. These are actually 70 new traced fragments. Those 8, these 17 residues can be separated in 8 new fragments that are NCS related. So actually those 4 fragments are in 1 monomer, 3 alpha helices, and 2 beta strands. So our next step was to try to improve this trace by modeling again the sidechains. So since we don't have a prior information to this missing N-terminal domain, we don't have the original sequence that we had in the remote in the LMTC structure, the C-terminal domain. So we developed a strategy that would match the secondary structure prediction on the sequence and the trace. So in this case, we used the software Aleph that Massimo talked about. We assigned this secondary structure on the trace fragments. It's always more difficult to assign secondary structure to a partial trace. Aleph does that. In here we have an example of the N-terminal sequence. We may use, for example, PsyPred. We predict the sequence what residues should be alpha helices and beta strand. This has been talked about yesterday. And in this case, we match the information from the beta strands into the hypothesis allowed by the secondary structure prediction in the sequence. So in this case, we have 4 residues for this red chain and 5 residues for this other chain. Since this 4 can be fitted into those 2 pieces of the sequence, those 2 hypotheses will be evaluated. In this case, the restriction given by the 5 residues will be evaluated only in this case. So again, we take the sliding window, which is the size of the chain. We slide it over the hypothesis allowed by the secondary structure prediction and sequence. We generate 2 hypotheses for the chain C, 4 hypotheses for the chain D. We do the same for the α-helices. Since the predicted sections on the sequence are bigger, we have a higher number of hypotheses. We applied such a strategy in LMTC, so this is the workflow. We have the secondary structure prediction. We usually calculate it with PsyPred. We have this secondary structure assignment with Aleph. We generate all of the hypotheses. In this case, we align those 2 informations to also filter, to reduce the number of possibilities. In this case, we have a lot of more possibilities, so we reduce it by seeing what is the, how are those hypotheses being fitted into this fragment. We filter those hypotheses, send it again to modeling, refinement, and density modification. So we applied such approach on LMTC, and we applied first on the strands because less number of possibilities was allowed. Given the restriction given this by this loop, we assigned either the first predicted strand with the second or the second with the third. We generated all of those hypotheses and push it through slider workflow. Here again we have identity versus LLG. We got a single solution distinguished from all of the rest. We expanded the best solutions. We were able to expand the strands. Then we went further, modeling the sidechains for the strands. So we evaluated this predicted helices into this 3 helices. Here it's important to highlight that the NCS, the non-crystallographic symmetry that is present in this C-terminal domain is different than the N-terminal domain. So when we were doing the trace, we couldn't input this restriction in the trace. That's because the hinge between these the domains in the first monomer and the second was different. So in this case, we already input the NCS while generating the hypothesis. So we generated the same hypothesis for both of the fragments, and this was important for the distinction of the hypothesis. And then we went further and further modeling the sidechains until the point that the electron density already revealed additional features, which could be used for other modeling softwares or done by hand. We have created different strategies. We can calculate through a brute force in a grid, where we calculated most of the sequence hypotheses. We are also having a special case, which we only model the hydrophobic residues. Those residues are usually buried, so they have lower B factor, they have less flexible, so they can influence differently the results. We are also performing a light version, which would be applied for a single machine, where we could only model the polyserine fragments. So shifting to my work in Brazil, I work usually in Brazil with toxinology, also with crystallography. So in such a cases, it's often we face the case that we know the enzyme fold, we crystallize the structure, we know its function by the functional assays, but we don't exactly know the sequence. Why is that? It's different from most of the fields. So usually we purified those proteins from the snake venom. So we actually separate those proteins, and they coexist as various isoforms because of the rapid evolutionary divergence and variability on the samples on these proteins. We have a lot of different isoforms. For example, here in beta-bungarotoxin and cretoxin, we have more than 15 different isoforms. So when we're trying to sequence them using mass spectrometry, we may not get a single sequence. We may get 50% of coverage. We are not exactly sure on what's the exactly residue type in those proteins, but we know the fold, so we can phase it. But when we are in the modeling, we are developing a strategy that instead of sliding horizontally, as I showed you before, we are sliding vertically. And so we have regions which we know from mass spectrometry or from phylogenetic analysis, which the residue should be. For example, if it's a catalytic site, if there's disulfide bridges, then we are sure on the sequence. And then in regions which we don't know, we perform this horizontal slide and started to assign residues and so on. So in summary, Slider uses the available knowledge of the sequence and partial trace to generate the most probable hypothesis of residue composition. This multi-hypothesis approach may reveal the rest of the structure. And LHG served as a form for us to distinguish the most probable hypothesis. And then we were able to elucidate 3 novel structures, and we plan to distribute Slider in CCP4 this year. I would like to acknowledge my supervisors, Isabel Zon and Marcos Fontes from Brazil, also my group in Botucatu in Brazil, my group in Barcelona, in special Ana Medina, Claudia and Massimo, who we have been discussing about this work, also our collaborators in the University of Cambridge, University of Göttingen, and also John Baxa and Ramon Hurtado's group, who provided us the unknown structures that we applied, sequence Slider. And thank you very much for your attention.